And the next speaker is Marcelo Pereyra from Heriot University, and he will talk about Bayesian inference with data-driven image priors. Please.
Thank you. Well, thank you very much for the invitation to talk and for organizing the seminar and all the additional work that you have done to make sure it can take place despite the particular situation. So this talk is joint work with some of my colleagues. So my PhD student Matt Kostas Sigalakis, who's a colleague at the Maxwell Institute, and Andres Almanza from Paris. So the the talk is structured in basically three parts. I have an introduction that hopefully will allow people who are not familiar with the area to learn more about the area. And if you find it too introductory, then well, I'm sorry. It's always difficult to calibrate talks, particularly when you can't see the audience. Then I'll have a part where I'll explain what's the contribution of our work, and then I'll report some experiments. So okay, so I'm interested in problems that arise in imaging sciences. So a simple example would be a situation where you want to observe some scene, say take a high resolution image, and because your camera is not perfect, what you observe is not equal to what you would have liked to measure. There's some degradation in the magnitude you wanted to measure. In this case, for instance, let's say that I'm a bit too far and my camera can't quite resolve the level of detail that I want. The same thing could be postulated for a different imaging device. It could be an MRI scanner, a CAT scanner, a PET machine, a radio telescope, whatever you want. And essentially, imaging scientists spend a large part of their time looking at ways of recovering the true scene from the observed image. So they come up with imaging methods that analyze the observed data to estimate the scene. And this is what we call an inverse problem, because our mathematical models, which are mainly derived from physics, are very good at explaining how the true scene becomes the observed image. So we have a lot of equations that go in this sense. So that's the easy way in which we can model the problem. In the inverse problem, we are trying to work with equations that point in the wrong direction. So they're inverse in that sense. At least that's how I usually understand it. And formally, what we're going to do is say, well, we're interested in recovering some magnitude. For the purpose of this talk, I'll call it X, and it's just a large Euclidean vector. And I don't measure X, I measure Y, and Y is related to X. And that's how I'm going to recover X from Y. So for the purpose of this talk, I'll assume that they're related by some mathematical model. And in most imaging problems, one can consider, at least as a first order approximation or something to start working with, a linear model of this form. What I'm going to present today is not constrained in any way to linear models of that form, but the experiments that we report are. So we assume that, for instance, that the observed data Y comes from the action of some operator A, in our case the camera, on the truth X, and then there's some perturbation or additive noise that is corrupting this model that would otherwise be deterministic. And this perturbation, it's something we don't know, so we can't quite describe how X became Y. We can only do it up to that unknown term W, which can represent genuinely unknown terms and can also represent modeling errors that may or not be known, but that in any case we're not including in the operator A, which represents our instrument. And systematically in imaging sciences, we operate in a situation where the recovery of X from Y is ill-conditioned or ill-posed. And this is in part because of the nature of the problems and in part because of how we approach them. So if we have a camera that can comfortably take images of resolution, say, of pixels of 1 centimeter times 1 centimeter will often want to operate at a level that is of higher resolution and then make the problem ill-posed. So we're systematically in situations where we want to use the instruments in a regime where they're not comfortable. And as a result, Y does not have the information that we need to recover X. And as a result, the problem is not well posed. So we have to regularize it to make it well posed. And regularizing it is, in a certain sense, introducing additional information to narrow down, the solution of the problem that we're interested in. and this is how we get away with the fact that we're pushing the instrument outside of its comfort region. So, if you're familiar at all with my work, you'll know that I'm very fond of the Bayesian statistical framework. So this is one of many frameworks that you can use to formulate this kind of inverse problems. And so this is essentially a probabilistic framework in which the unknown image that you don't know, you represent it as a random quantity, and then you use probability distributions to model its expected properties, and you use a probability distribution to model the relationship between the data you have observed and X, and that's how you go about performing inferences. Everything is based on this joint statistical model P of X and Y that tells you the relationship between what you know and what you don't know. And once you have your equations, when you have written down your model, something particularly beautiful about the Bayesian statistical framework is that it comes with a very powerful decision theory. So, once you have your model, you can ask questions to this model that you formulate them in terms of decision problems, and then apply rules of probability and decision theory and get the answer to your question. So I'll show lots of examples of that in a few minutes. So the statistical model that we use, the joint probability distribution relating X and Y, has two key ingredients: the likelihood, which is the conditional distribution of the data given X, and this is essentially the statistical model associated with our forward model. So the fact that a true image X will get degraded in a specific way and contaminated with some unknown perturbation that can have some specific distribution, and that will lead to a specific distribution for the data. And this is the model that is not written in the right sense, in the right direction, because it is a model that tells you this is, these are the probabilities associated to observing different data sets, given that the truth is X. Well, I know exactly what data set I observed. What I don't know is X. So this model on its own is not very useful. I don't know the truth. I can never evaluate this in a meaningful way on its own in this setting. And then we have the prior distribution, which is essentially the marginal of X. So it's what comes when you marginalize out the data from your joint model. And this models expected properties of the solution. So in a very simple case, this could model that X is sparse, or that X is piecewise regular, or that X has wavelet coefficients that look in a certain way. In this talk, I'll go into more advanced models that capture information from training examples. Now, something important is that in imaging problems, this likelihood term is not useful on its own because it has significant identifiability issues. So you can't narrow down solutions in a sensible way by using just the likelihood. So you really need the prior P of X to regularize your estimation problem, make it well posed, and deliver meaningful solutions. Otherwise, the uncertainty in the solutions is huge. So if there are any statisticians in the audience, other than a few that I know are attending, this is a big difference with respect to traditional statistics. Here, the prior is very influential, and even if your image is large and you have a lot of data, the prior will remain always very influential. There is no concentration of the posterior in the very simple ways. There's concentration in other ways, but it's far from straightforward. Okay, so once we have specified a joint model P of X and Y, we're going to derive the posterior distribution P of X given Y by taking the joint divided by the marginal of Y. Now the marginal of Y, this is the marginal likelihood of the data, is something that usually doesn't appear at all unless you are approaching your problem in a Bayesian statistical framework. P of X and Y, does appear even if you formulate this in another setting, particularly in a variational optimization setting, because you have terms that look like data fidelity terms and you have terms that look like regularizers. So until that point, there's lots of links that you can establish. But once you normalize your posterior distribution with P of Y, then you start having some elements that are genuinely, from the Bayesian or statistical formulation. And we'll see that this term here that normalizes the posterior is very useful because it provides an indication of the goodness of fit of the model. And this is something that I'll explain in a minute why it is important and how you might want to use it. Now, this conditional distribution X given Y, the posterior, models our knowledge about the solutions given the data. And I have stressed in the slides the term models because none of these probability distributions are true. I don't know what they are. I have to write down equations and then play with them. So, in a certain way, you make certain modeling assumptions and then you use them, and they are useful to the extent that they are useful. If your equations are not good, then the answers that you get are not useful. That's all. There's nothing, true, correct, or incorrect about any of these probability models. Now, once you have postulated this, then you will derive your inferences using Bayesian decision theory. And something that is quite nice is that, well, not only you have a nice theory for your inferences, but also this is very clear, modular, and tractable. I know exactly what each element of my statistical model is contributing. One term is describing how the truth is related to the measurements. One term is describing properties of the truth on its own. One term is describing properties of the measurements on their own. And this gives me a tractability that you don't have, for instance, if you address your inverse problem with an end-to-end neural network. Okay, so why are Bayesian statistics not widely used in imaging if they have all these benefits? Well, because there's three main challenges that were identified in the 70s and 80s and that are still challenges today. First of all, computation is non-trivial. Computing probabilities and expectations is challenging. Algorithms became faster, but then images became huge. And now over the last maybe 5 years, algorithms have started catching up again. There's a lot of research on faster faster algorithms that in many senses are close to optimization algorithms in probability spaces. So those are, that's an area where we are seeing a lot of progress. Then Bayesian analysis is another problem. Imaging scientists are not used to asking questions in terms of Bayesian decision theory. So we don't always know what questions to ask to probability distributions in order to obtain an answer that is meaningful from an imaging sciences perspective. So even if we compute the posterior, we don't always know what to do with it. And the third main challenge is Bayesian models. So if our models are too simple, then they can't support advanced inferences. And I've worked for a long time on accelerating Bayesian computation for models that are log concave with priors that look like total variation or sparsity. And now we can compute interesting quantities for these models, and we're starting to know which questions to ask. But it's still not clear that the model would provide the right answer because the model is too simple. So now we're conducting experiments to try to see what inferences those models can support and what inferences they're just not able to support because they are too simple. So the aim of this talk is to consider a slightly different setting in which your prior is data-driven in the sense that you have a lot of training examples. Okay, so the idea is that instead of trying to specify the prior analytically by saying, okay, I'm going to promote solutions with low total variation or low, or that are close to sparse, what I'll say is, well, I have this huge library of clean images, of examples that I can use to learn my prior P of X, or that I can use, that's my prior knowledge. So I want this to represent my prior knowledge. I have a set of samples that I assume to be, ID examples of, the prior distribution P of X. And X, the unknown solution to my problem, is also a sample from this distribution, but I have not seen it yet. And what I have seen is Y, that is related to X through P of Y given X. So the question is, how can I combine these two things to perform inference with the posterior distribution of X given Y and all my other examples? And importantly, the likelihood P of Y given X, I want to keep it analytical. I want to be able to write it down explicitly, and I want to be able to change any elements, change the operator A, change the noise level, whatever I want, without having to change in any way my prior. I want to learn my prior, do it once, and then be able to combine it with any likelihood, or potentially address likelihoods that have unknown elements and estimate them jointly, without having to touch the prior in any way, because that's one of the main ingredients of Bayesian inference. There's a very clear decoupling between the conditional of Y given X and the marginal of X. These are two different things, conceptually different. So, they should stay different all the way through. So that's the idea. It's how can you, say use a neural network to learn your prior in a way that you can then combine with a likelihood to derive this posterior distribution in a way that preserves modularity, interpretability, and that enables efficient Bayesian computation. There's lots of ways in which I could construct this using just standard tools from computational statistics, even importance sampling, which is an algorithm that has been known for 50 years. But if I did that, it would not scale efficiently in high dimensions. It would perform very poorly. So the idea is to do it in a way that then allows efficient Bayesian computation. So we're exploring different ways of doing this at the moment, and this talk is about one specific way, which has its advantages and disadvantages. So in this talk, I'm going to assume that X lives close to a low-dimensional submanifold of its ambient space. Okay, so I'm going to adopt the manifold hypothesis, and yeah, so the idea is, although X takes values in this large vector space, most of the probability mass should be very close to a low-dimensional submanifold. So if I could learn that submanifold, that would be great, because I would be operating in a space of much smaller dimension. Just reducing dimensionality would significantly regularize my estimation problem, particularly if I start operating at a level that is much smaller than the size of the measurement vector Y. And if I can either specify myself or learn the distribution of X on the manifold, then that I could have a prior on the manifold and then perform my Bayesian inferences on the manifold and so forth. So that's what we're going to do. We're going to estimate a new parametrization for X, a new representation, a latent representation that I call Z, of dimension much smaller than X. And I'm going to estimate a mapping phi that takes me from Z to X. And there's infinite mappings that I could come up with. And to narrow it down to a specific one, I'm going to say that Z has to be a Gaussian random vector. So I'm going to specify the marginal of Z, and now that gives me just one mapping phi that will push forward Z into the ambient space of X in a way that agrees with the empirical distribution of my samples. Okay, so I am now going to operate on this latent space Z, and the mapping that takes me from Z to X has to be estimated in a way that is in agreement with our training examples, in a way that explains as best as possible the training examples that I have. So, okay, now suppose that we do that and we obtain phi, then the likelihood of P of Z given, Y given Z is simply the likelihood of P of Y given X evaluated at, that specific point X that I obtained by, taking Z and moving it to the ambient space through phi. And with that, I can then simply write my posterior distribution. The prior on Z is Gaussian because I specified it that way. The likelihood of Y given Z now involves my change of variables through phi. And this posterior distribution might be very complicated, but it will be low dimensional. In low dimensions, I will be able to get away with complicated distributions. Also importantly, although I don't have time to explain it in my talk, it's very easy to show that this posterior distribution is well posed and that moments exist. So I can easily show that if I want to compute the posterior mean, it exists. If I want to compute a posterior covariance, it exists. So these are important things that we don't get with some other methods that I'll discuss a bit later. And then once you have that posterior distribution, you can push it through phi to get the posterior distribution of X given Y, which was the posterior distribution you were originally interested in. So there's different ways of estimating phi. Luckily for us, this is a problem that has been studied quite extensively in the machine learning literature over the last, say, 6-7 years. In particular, there's two lines of work, one on variational autoencoders and one on generative adversarial networks that state the problem in slightly different ways, but they both give you at the end a mapping phi that verifies more or less what we want. And we played a bit with both and arrived to the conclusion that at least experiments that that we're doing at the moment, VAEs give better results. So that's what we're using at the moment, but there's nothing fundamentally important about how you do it. In my talk, I just assume that you have a way of learning this mapping. If tomorrow, or someone came up with a much better way of learning phi, we could straightforwardly adopt it. So the idea is that, okay, you are specifying the marginal of Z. Z is Gaussian, and then you're going to say that X comes from a statistical model that is parametrized by Z. This is always true. You can always do this. Now, the model that parameterizes Z, so the model for X parameterized by Z is unknown, and you could come up with something complicated for it, but because the problem is difficult, we're going to stay with something simple. We're simply going to parameterize it as a Gaussian distribution with some mean mu X computed from Z and some covariance computed from Z. And then the objective is to identify these two functions so that when I generate samples from this, they agree with the samples that I have observed, my training examples. So we are going to parameterize these unknown functions with neural networks, and we're going to learn their weights or estimate their weights so that they are in agreement with the data. In particular, we'll do it by maximum likelihood estimation, which is a standard strategy in statistics. The likelihood itself is intractable, but we can lower bound it and maximize the lower bound. And this is a standard strategy in variational Bayes. So what I'm going to do is, okay, so by the way, none of these ideas are new. They are explained in several places, but in particular, you can read this tutorial by Kingma. And the idea is you come up with this lower bound, and the lower bound involves another network that we call the encoder, which is the network that allows you to reduce X to the latent representation Z, and it is also a statistical model. And then you try to learn both, these two representations, the two networks, the encoder and the decoder, decoder, such that encoded, decoded samples are disturbed as little as possible, and that when they are encoded, their latent representation Z is Gaussian. Okay, so that the marginal distribution of Z stays Gaussian. That's how you narrow it down to one specific encoder-decoder couple. And once we have, learned this by using Adam, for instance, then we take as phi the mean of the decoder. Okay, so the network mu x of Z, that's what we use as our mapping. That's what we have used in this work. Now, that allows me to specify my posterior, but it does not, tell me how to compute expectations and probabilities with respect to the posterior. So in this talk, we're going to use a Metropolis Hastings algorithm to draw samples. In particular, we're going to use the precondition Craig-Nicholson algorithm, which is a flavor of Metropolis Hastings that is particularly well suited for models that can be written as a change of variables from a Gaussian measure. Because we have a Gaussian prior, we can very easily write it that way. It is a Metropolis Hastings algorithm that is well defined in infinite dimensions. It's slow, it is infinite dimensional, but it's still fairly slow, but it's robust. And because we have lots of other ingredients in this work that make the posterior difficult, we decided to go with a very robust algorithm. We also have faster algorithms that we're finishing now, but it's important to have a benchmark to make sure that they're computing the correct quantities. So here what we are presenting is that benchmark algorithm, and it's an algorithm that not only has this metropolized step that makes it more reliable, but in addition, we run lots of parallel Markov chains. So the way we do it is we don't only have one Markov chain targeting the posterior, we also have a Markov chain targeting the prior, which is very easy to sample, it's just a Gaussian. And then we have m-1 intermediate models that bridge between those two, that you can think as approximations that go from the prior to the posterior. And because the prior is very easy to sample, those intermediate posteriors will allow us to deal with things like multimodality. Even if the posterior is very multimodal, we can always jump between modes by doing this bridging. So this is a standard strategy in computational statistics that we don't use a lot in imaging, because in imaging it would be expensive if we were operating in the ambient dimension of X. But because here we reduce dimensionality, it is not bad. And then we can get the samples from X by pushing samples of Z through phi. And we are developing faster algorithms that are a good 2 orders of magnitude faster, but they require some work. Off-the-shelf algorithms, gradient-based off-the-shelf algorithms don't work very well. Well, for a simple reason that they require things like Lipschitz smoothness. And these models, because of the neural network inside, they don't necessarily have the kinds of Lipschitz constants that we would like. So we have to work a bit on them. So this is not the first work to try to learn a prior from data and perform Bayesian inference. There's quite a few. In particular, there's a recent paper by Mario Gonzalez and his co-authors that has a similar setup, but in an optimization formulation. And what they want to compute is the joint map estimator of X and Z. They do things slightly different, but the spirit is similar. The main difference is that it is always in an optimization formulation with a very clear goal of just computing a point estimate. And then this is also related to work that Jonas Adler and Ozan Oktem and Bangji and Sam did recently on trying to train GANs to learn the posterior distribution. Our work is quite different in that we are learning the prior, not the posterior. We're combining the likelihood analytically, and although we won't have the high dimensional results that they have, we do have a lot more understanding and theoretical guarantees on our method. So I'll show that in a minute. More generally, there's a large literature on data-driven regularization schemes. You can see this Acta Numerica paper that appeared last year. And otherwise, there is a very interesting paper from 1994 2005 by Julian Besak, Peter Green, and Hindon and Karen Morgensen, where they talk about Bayesian inference in imaging models, and many of the ideas that they had were unfeasible back then, but what we're doing is not too far. Okay, so now I'm going to show the experiments. So we're staying with MNIST, which is unfortunately, but that's what we're doing so far. It's a good, simple training example to see that the method is working or not. In our experiment, we're using 10 parallel chains, a lot of MCMC iterations, in total something like 1 million, combining all the chains. And the computing times are of the order of 2 minutes to 10 minutes, depending on the imaging problem. So it's absolutely feasible, but if I wanted to do it on a large image, I would need one of these new MCMC algorithms that we're developing. And we compare with the state-of-the-art method of Mario Gonzalez from last year, and also with a standard ADMM algorithm used in a plug-and-play fashion with a denoiser that is specialized for MNIST. Okay, a neural network that will learn with MNIST to denoise. Okay. Okay, important advantage of our method. We can very easily identify the dimensionality of the latent space. Because we're specifying the marginal for Z, we're saying Z has to have this specific mean and covariance structure. We can learn models of different dimensions and then check for key statistics, in particular the trace of the covariance. And once you reach, in this case, dimension 12, you see that increasing dimensionality, doesn't follow what your model is predicting. And this means that the marginal that you're getting on Z is not the one you specified. In fact, it's a Gaussian that is degenerating. So, these are empty dimensions. So for MNIST, the manifold hypothesis is fairly true. And this is something that is well documented in the literature. We're not the ones that discovered that MNIST is close to a submanifold. So we're going to use dimension 12. So we're going down from an image of dimension 700 and something to 12, which is very manageable. Okay, and this is the result that you get on different problems. So here is denoising, 3 noise conditions. The last one is very aggressive denoising. We have a PSNR of -8. And and we see that our estimates are fairly good. We are computing the minimum mean square error solution, so the posterior mean, and then pushing it through phi. The joint map performs well when the noise level is not as aggressive, but it has a point where it breaks, whereas the point where we break is a bit lower. And then if you just did plug and play ADMM, even with a very good denoiser for MNIST, your results would be worse. They would break much earlier. We observe the same thing in deblurring. So this is quite aggressive deblurring. The blur has size more or less 5 by 5 or 6 by 6. And the image is 28 by 28. So it's a big blur. And there's quite a lot of noise. And again, we see that they are fairly robust to this problem that is very poorly posed, and that the other methods break a bit earlier. They're still performing very well. Joint map performs very well, but it can't handle noise conditions that are as aggressive as we can. And that's just because we're computing a much better estimator. We're computing the posterior mean, which is a much better estimator than the joint map in this problem, where in addition, you have non-convexity and a number of other things that make the problem difficult. And then, of course, plug-and-play ADMM is struggling as well. And this is in painting with 75% of randomly missing pixels. This problem is not as ill-posed, even though it is missing a lot of pixels. We know that there's a lot of algorithms that can deal with it. So we can deal with it quite well, even in aggressive noise conditions. Joint map as well. The reconstruction is a bit worse, but in painting, it doesn't seem to be so important. It would be interesting to structure the in-painting pattern and see what happens. We expect that all methods will deteriorate. Hopefully, ours a bit less than the others. Okay, so that's reconstruction. What I really wanted to present, and that's how I'll conclude my talk in the the 5 minutes that I have left, is uncertainty quantification and
Excuse me, Marcelo. Excuse me.
Yes?
You should speed up. 5 minutes will allow just for 5 minutes of questions. So it would be nice if you could do it shorter than 5 minutes.
Okay, well, 3 minutes. So okay, so a few key ideas that that you can do if you adopt a fully Bayesian solution, as opposed to just stopping at point estimation, which you could do with optimization instead of sampling. For instance, uncertainty visualization. What we did is we identified the two directions in the subspace where the covariance is most spread. So these are the two directions in the subspace where you have a worse uncertainty, and then we did a grid of solutions. So what you observe are the kinds of solutions that here that are within a 95% confidence region in that subspace. And we see a lot of number 4s, a few number 9s, but in any case, that gives you an idea of the variability of the solution that you can have. I won't talk more about this because of lack of time, but the more your problem is ill-posed, the more you see variability in your solutions. So this is this is a way in which you can visualize uncertainty. Important thing: models that are data-driven can be severely misspecified. Why? Because you are using millions of training examples or thousands, and then one single observed measurement that is not even well-posed. So your prior can override your likelihood, and you can have a Bayesian model that is very misspecified simply because the truth that you're trying to recover is different from your training example. So it's very important to do a misspecification diagnosis test and make sure that your model is well-posed. So we do that by using a sort of like a likelihood ratio test that you can read in detail in the paper that will hopefully be on archive in a few days. And then you can get a null hypothesis, which is the blue distribution for our marginal likelihood, which is the statistic we're using. And then we use this other data set, not MNIST, and computed the likelihood for that. And what you observe is that the likelihood values that you get are a lot smaller. So you can do a hypothesis test and reject your model. So I can test before analyzing the data set, before reporting a solution, if my model can analyze that or not. And with very good powers of the order of 99% for some problems. I think deblurring or in painting is a bit more difficult. We have a power of 90%. But still, I can tell you this is not a digit from MNIST. Okay, so this is something that we should be systematically doing if we're using this kind of aggressive priors. And then finally, and this is, in my opinion, a very interesting result, we're checking whether the Bayesian model is correct or not in a frequentist setting. If I give you a probability and I say the probability of this is 99%, is this probability true or not in a frequentist setting? So that means if you were to repeat this experiment 1,000,000 times, would you observe that in 99% of the cases, what I said was true if I said it was true or not? So that's, checking if the Bayesian probability is correct in a frequentist setting. And we did this experiments for in-painting and denoising, and we check, coverage, which is, the statistical sense for this question. And what we observe is very good agreement between Bayesian probabilities and the truth. It looks like in the second plot, they are a bit different, but this is very, very close to the truth compared to what you would get with any other kind of model. So, in our experience, this is, to our knowledge, this is the first time that we have a Bayesian model that is accurate, that has accurate coverage properties for an imaging problem, although it is a simple, imaging data set. This is a case where if you said this tumor has probability 99% of being there, then your probability 99% is meaningful in a frequentist sense. I'll stop there. Thank you very much.